Okay. All right. So this is the last of the 3 lectures that Alexander is doing on the spaces with curvature bounded above. It's part 3. Please, Alexander, go ahead.
So thank you very much. Yeah, we proceed. So, yeah, so I'm going to talk about special class of spaces with curvature bounded above. In this class, yeah, so this is a class in which one can say something about topology, so much more than in general. So for general spaces with curvature bounded above, one can hardly say something but that they have some dimension, and this top dimension one can find some Euclidean subsets which are not open in it, but yeah, topologically embedded. But one cannot say more. So, and the class of spaces I'm going to talk about, they have similarities with Alexandrov spaces. So the definition, we call a space geodesically complete if no geodesic terminates in it. So if something like this does not happen, so that you start with a geodesic, it runs, and then it comes to a point and cannot be extended as a local geodesic, say. So this we do not want. And we say that a space is GCBA, so it's geodesically complete and has curvature bound above if it is locally cut kappa, so it has curvature bound above, it is locally compact and geodesically complete. So this assumption of being locally compact is also needed, so in order to get some meaningful results. So just if you start with any, say, cut zero space, and then you attach to each point array, then the rising space is geodesically complete. So, and as complicated as your space was at the beginning, yeah, will be even more complicated. Okay, so the first observation I want to say, so that the whole theory I'm going to talk about is local. So it's about the local structure of such spaces, and the assumptions are also local, but in fact, one can replace a small neighborhood of any point. One can change a metric by a conformal change so that it becomes complete, and you can change cut. So if it was cut 1, then it becomes cut 0. So, but it's again, so it's very locally. So if you are on a cut 1 space and globally, you cannot change the metric, so it becomes cut 0. So it must not be.
Could I interrupt with a quick question?
Yes.
So, of course, in Riemannian geometry, there's the distinction between a geodesic that's merely inextendable and one that's complete. Do you have a preferred parameterization here, so that, like an arc length parameterization?
Yes, it's proportional to arc length.
I see.
So any Riemannian manifold would be geodesically complete in this sense. Even if it is even a non-complete one would be geodesically complete for this definition.
Yeah, so your definition is actually a geodesic that maps the entire real line to the space, does not terminate. No. So the statement is that you cannot. Okay. So the assumption is that there is no geodesic defined on a compact interval, which cannot be extended to one direction. Yes.
So say an open interval is allowed and the closed interval is forbidden.
I see. So an open, a geodesic defined on a bounded but open bounded interval that is not extendable, that would be considered complete here.
Yes. But again, so once you so you can change from the local picture to the global one, and then the assumption would be that any geodesic is extendable to a complete geodesic defined in the whole real line.
I see.
So this would be the geodesic completeness as you know it in the Riemannian geometry, and this is essentially the assumption we can work with. Okay. So the assumption I made was slightly. Yeah, it was a local one, so because the whole theory is local, but you can, but you can assume that that you have this global assumption.
I see. Okay, thank you.
Yes.
Okay, so what is the aim? So what do we want? What do we can hope to achieve? So we want to prove that our space is similar in a sense to a simplicial complex with no free faces. So no free faces bedeutet so that there is no maximal face like in this triangle. So in this triangle, so each side is a free face. So free face means there's only one maximal simplex adjacent to it. So if you have this picture, then so this middle edge is not free, but there are many other free faces. So it's an easy observation that if you take a simplicial complex and you equip it with a piecewise, with a metric of piecewise constant curvature, then geodesic completeness is equivalent. So if it is a cut one space, then geodesic completeness is equivalent to this assumption that there are no free faces. So now the first observation is that we cannot expect more. Why? This is a result of Berestovsky. There is a result of Berestovsky and Gromov. I have already mentioned that on any so if you take any simplicial complex, then you can equip it with a metric which is cut one, such that each simplex has constant curvature 1. So you cannot reach more. So this is very different from the theory of Alexandrov spaces, where the presence of any lower curvature bound, so even lower curvature bound -1, already provides a very strong restriction on topology. So for instance, say in dimension 2, the only Alexandrov spaces are the manifolds with boundary. So on the other hand, here you can have any complex. So in fact, in dimension 1, this is exactly what we get. So if X is one-dimensional, then it is a GCBA if and only if it is locally a finite graph. So it looks something like this. So, and if it is cut 1, if it is cut 0 really, then it is a 3. So already in dimension 2, the situation is more complicated. So the example one should have in mind, the one which has been observed by Kleiner. So we have learned by the theorem of Lytchak that it's possible to glue cut spaces along convex sets. Now, sometimes, say in dimension 2, one can make it very precise. One can glue spaces also along not convex subsets, but along subsets with controlled curvature. So we choose the following 2 curves on the plane, which are symmetric along the axis, and now we take one half plane and glue it along the upper curve, and we take another half plane and we glue it along the lower curve. And then if the curves, so now one has to be a little bit careful how you glue, but one can do it so that the rising space is cut 0. And then around this point where the curves converge in a non-simplicial matter, around this point you have no triangulation of your space. So this already happens in dimension 2. And in fact, the situation is not much worse. So there's a recent result by Nagano, Shoei, and Yamaguchi showing that essentially all CAD spaces of dimension 2, so also all GCBAs of dimension 2 arise in this fashion. Are there questions? So we want to prove that the space is similar to a simplicial complex, but so we cannot quite expect that it is simplicial complex, but we can try to see how far we can get. So this is also, so this example, I should also say, so this is in contrast to lower curvature bound, so there the spaces have much tamer topological structure. So this is a famous result of Perelman. Okay. So here are the goals.
Sorry, can I ask a question? What is
Yes,
the dimension here? What is the notion of dimension?
The notion of dimension, so this is the dimension I have mentioned last time. So there are, so for cut spaces, all dimensions, so if you, so all dimensions by the Hausdorff, so are equal. So say it's a topological dimension. Or you can say it is the dimension of the maximal subset homeomorphic to Euclidean ball, which you can topologically embed into your space, which might not be open.
Okay, thank you.
So, but in fact, so in the setting of GCBA, so the dimension is, it's also, much better visible what it is. So the first result is that the topological dimension of a GCBA. Okay, so everything I'm going to say from now on is about GCBA spaces. So about spaces with curvature bound above, locally compact, and geodesically complete. So first observation is, so the topological dimension equals the Hausdorff dimension, and there is a large regular part. And this large regular part, so this largeness in the sense of the, say, Hausdorff measure, and this large part is a Riemannian manifold. It's non-smooth, but it's with a controlled Riemannian metric. It's a controlled smoothness. So it has been already known before my work with Koichi Nagano, so there was an unpublished work by also Shoei. So here I should say that already this result is completely wrong also, in dimension 1 already without extendable geodesic. So the basic example is, so you can take, you can find a compact graph, so compact tree, if you choose the branchings, in a precise way, so then you can achieve that the Hausdorff dimension can be as large as you want. So you can even choose it to be infinite. Yeah, but this cannot happen if if the space is geodesically complete. So if you can, so if any branch you choose, you have to extend to a whole ray. So this immediately shows that if you, that if you want to stay locally compact, then there are only finitely many branchings in a compact region, in one-dimensional situation. So, as I have mentioned, so there are similar, stronger results even for curvature, for space with curvature bound above. So it's due to Bragg-Gromov Perelman and then the Perelman, and there are similar results for some RCD spaces. So this is what one very often tries to prove. So this metric geometry, so to prove that, or at least on so there's a large regular part, and this regular part is, it's close to what you, to Riemannian geometry. Okay. So are there questions so far?
I have a comment though.
Yes.
In RCD spaces, well, there are various notions of dimensions, and sometimes Hausdorff dimensions can be bigger than sort of the natural dimension.
But I said so for some RCD spaces. So for this top dimensional ones,
so there are recent examples by Wei and Payne that show that Hausdorff dimension can actually be bigger than the topological one.
But these are not top dimension. So these are not collapsed. Yeah, these are not. These are collapsed spaces. No.
So those spaces are collapsed, right?
Yeah. Thanks. Okay. So second part of the goal. So this was about regular part. Now the second part of the goal. So this is also very typical for from the stations of some spaces, beyond Riemann manifold. So you want to say so that you can structure the singularity. So say there's a regular part and there's some less regular part and less regular part, and so that the less regular the part is, the smaller it should be. So it's statement. So there is a stratification of your space, and here stratification. So it's not really. So it's not a division in topological manifolds. So these are just closed subsets. So they have some. So you can say more about it. But So and for any x in the complement of xk minus 1, a neighborhood of this point. Essentially, so in a sense, it splits off an RK. So it looks, in a precise sense, similar to a product of a k-dimensional Euclidean space with some factor. So I will say a little bit what this almost splitting means, but not being very precise. So and so the point is so that the set of points which do not admit such a k splitting, topological and metrical, it has dimension at most k. So and what one should think of, so think of So you should think of xk as the cave skeleton of your space. So if you have a simplicial complex, then along the edge you can split off the Euclidean line, but not a Euclidean 2 space. And in a vertex you cannot split off nothing. So this would be a point in x0. This would be x1, and the faces would be x2. So this is another goal. And so the final class of, so the final part of goals I want to say is topological regularity. So this thing. So we already know that so that any such GCBA space has a large part which is Riemannian manifold, and one cannot say much more usually, but sometimes you can try to ask, okay, so if it's not maybe smooth, if it's maybe different from a smooth manifold, it can be, can you say if it's topological a manifold? So, and here's the theorem. So if the space is, so space is a manifold if and only if the space of direction is a homotopy sphere for all x, and equivalently if and only if so the tangent spaces are Euclidean spaces for all points. And using this result, so one has applications for limits of Riemannian manifolds and some sphere theorem. So for instance, one can show so that the limit of Riemannian manifolds, if you have a Gromov-Hausdorff limit, and all manifolds have curvature bounded from above, injectivity radius bounded from below, and they converge to something, then this limiting space is again topological. And you can say even a little bit more. So this is a version, so a weak version of a stability theorem of Perelman in Alexandrov geometry. And the final, yeah.
What kind of manifold?
It's just a topological manifold. So it is just locally homeomorphic to Euclidean space.
And I have one more question. So for cat zero, this theory is empty, right?
No, for cat zero, this theory is not empty. So what do you mean by that? What kind of manifold can it be? This is
I mean, because last time you said that it would be contractible.
Yes. So okay. So what I should say is, so that everything more or less until now are local results. So now it's maybe related to your question. So it's this global result I want to say. So let X be cat zero if it's a 4 manifold and X is homeomorphic to R4. So this is a global result. But in fact, so the proof is rather yeah, it's local mostly. So immediately you see that so any cat zero space is contractible, that there are a lot more contractible manifolds than Euclidean space.
Sorry, can I ask the question about the previous theorem?
Yeah.
Sigma X is required to only be homotopy sphere, or
yes.
It doesn't have to be actual sphere.
Yes, so yeah, it may look a bit strange if you see it for the first time. Yes, so the point is it does not need to be homeomorphic to a sphere. So the point is,
And it doesn't even need to be a manifold, right?
It does not even need to. It does not have to be a manifold. So if it's a manifold, then it's.
I know such example exists in CBP,
but conjecture. Yeah. So I can make an example. So this example, yeah, it's also so. Well, you have the same example also for Alexandrov geometry. The example goes like this. So you take sigma to be the Poincare sphere.
Right.
Poincare sphere. So this is a 3-dimensional manifold which has the homology of a sphere but is not simply connected. And now what you do, so you take the double suspension of this Poincare sphere. Now, if you equip this, so if you rescale it, so you just equip it with some metric, so that say with round metric, then the curvature is at most 1. The injectivity radius can be small, so you rescale it, so the injectivity radius is large enough. Then it's a cut 1 space. If you take the suspension over it, it stays cut 1. If you take double suspension, it still stays cut 1. So this double suspension of this space, this is a cut 1 space. Now, this is not very surprising. What is surprising?
So there is a question in the chat if, okay.
Maybe, okay, so
yes,
what is surprising? So this is clearly a 5-dimensional simplicial complex. Now, what is surprising is that this is homeomorphic to S5. So despite this fact that this sigma 3 is not manifold, if you take the double suspension, you get the topological sphere. Now, in this topological sphere, you have a singular circle. This is the circle along which you have the suspension, and at any point of this circle, so you have here some S1 sitting in this S5, and for any X in this S5, the space of direction is just the suspension, so just the ones, suspension of your original Poincare sphere. And this suspension, it's simply connected as any suspension of a connected space, but it is not a manifold. It's not a form manifold. So it's homotopy equivalent to the sphere, but it is not a manifold. Okay.
Yeah, so somebody is asking in the chat if there is a similar result for CBB, and yes, there is.
Yes, so there is a similar result for CBB spaces, so exactly the same one, but for CBB spaces, so for space with curvature bound above, this result is a is a trivial consequence modulo some known results in geometric topology of the local conicality theorem of Perelman. So this local conicality theorem of Perelman tells you that for any CBB space, a neighborhood of any point is homeomorphic to the tangent cone, so to the Euclidean cone over the space of direction. However, this is wrong. This is completely wrong in so for GCBA spaces. The example, so this example of Kleiner, which I have done at the beginning, so it is not so round. So there's this singular point. This very singular point, the space of direction, is a finite graph. So, but the space itself, so no neighborhood of this point admits any triangulation. Does it answer the question? So also the question about cut-zero spaces. Yeah?
I meant if X is compact, then it's empty. Stay. Right?
Yeah, exactly. So if X would be compact, So for compact, So compact GCBA spaces do not exist. Yeah. So just because for compact GCBA spaces, no, they would not exist if they are cut-zero. So they can be locally cut-zero, but for cut-zero, so you would need to have an infinite geodesic. So by the way, so there is a result of very different nature, so of combinatorial nature, which I don't quite understand, but it says the following. So you can say precisely, so which simplicial complexes so carry a piecewise Euclidean cut-zero metric. And up to subdivision, these are exactly the so-called collapsible complexes. So this is, so when you learn, so if you don't know what collapsible is, then forget this remark. But if you learn what collapsible is, then the example of a non-collapsible something you see is something like this Dunn's head. So it is contractible, but it's contractible for a weird reason. And so for cut-zero spaces, it turns out to be related to this collapsibility. Are there more questions here? So these are the results. Now I don't want really to provide proofs. I want to give some tools which I use. So and these tools, they are they are of very general nature. So they are used also in, say, in Alexandrov spaces, essentially in a similar way. So the first observation, very important one, so that the space is locally doubling. So meaning that you can find, so if you stick to a neighborhood of some point, then you can find some number such that any ball of radius r you can cover, so within this neighborhood, you can cover by this number of balls of radius r half. So it tells you that your space at any scale has the same compactness property. And this is due just to the following observation, so that you have, so that if you go along geodesics, then you grow and your space grow at least in the way as Euclidean space grows. So if in a neighborhood of some point you find too many points, then you also find many points on a large scale. Yeah, just going along these geodesics. So, and it tells you that if you know some compactness of some ball, then on all smaller balls, you are even more compact. So this is a very, powerful observation. It's very, yeah, it's very elementary. Now, in particular, so you can stay in a point and zoom in even more, and then at any scale, so you have uniform compactness, so you can go to a limit, and in fact, so this limit exists, and it is this tangent cone, so the cone over the space of direction. So this is really a Euclidean cone. Euclidean cone. Euclidean cone. So, and now you have so this following very trivial observation. So in Euclidean cone, you have here the origin of your cone, and for any other 2 points, let's say y and z, this triangle is Euclidean. So it's isometric to the Euclidean triangle. And this has now, if you zoom in and you have this convergence, so it's a Gromhausdorff convergence, so not all quantities need to be preserved, but there is some semi-continuity under this convergence. So I don't want to be precise what semi-continuity is, but you can show so that if you converge to something which is Euclidean, then nearby you are almost Euclidean. So it tells you that in X, so if you fix your vertex X, then for a sufficiently close point to the point X, your triangle is almost Euclidean. So, and you can say that it's almost Euclidean, so in any reasonable sense. So for instance, the angles are sufficiently close to Euclidean angles. Yeah. So in particular, so it tells you that if you have here your point X, then it may happen that the geodesics branch also close to your point. But this branching must occur along smaller and smaller angles. So it cannot happen what happens, say, in this first example of a widely branching tree, that you can, even close to your point, you have a branching at angle pi. Yeah. So this is actually, so this is the basic building block for all observations. Is it okay? So now the next tool, this is also widely used, so also, yeah, same way as it is used in Alexandrov Geometry. So in fact, I should say so that in large parts of what I did with Lytchak, so was just following the path like Burago.
Can I ask a vague question?
Please, please.
About the previous slide. So
Yeah.
if you have some point X where the angle is very large because it has many components. How can making it local make it Euclidean?
Yeah. So here is the point. So I'm not claiming that all triangles in a neighborhood are almost Euclidean. I say that all triangles with vertex equal to X. So say if you have such a picture, then even so if this is your X, then close to this point you have this triangle Y, Z1, Z2, which is very non-Euclidean. Yeah, so which is very wide. But say at this point, so any triangle with vertex X, this is a degenerate Euclidean triangle, which is sufficiently small. So on a graph, if you fix a point, it's a finite graph, then any triangle with X as a vertex is just a segment.
Okay, thank you.
So it's less than locals. So it's really a local statement with a fixed vertex. Okay. So now the next two is distance maps. So so in particular, so we want to prove that on some regular path, our space is a manifold. So to say that it is a Riemannian manifold, we need to find some good coordinates. So, we find these coordinates. So mostly these coordinates originate in some kind of distance map. Sometimes one has to do something with these functions, but essentially these are distance functions to points. So now the first observation is that this distance function to the point x almost splits in a small neighborhood of this ball, of this point outside of this point. So this is just, again, I don't want to be precise here, but this is more or less the statement I said before. So in the Euclidean cone, along any point outside of your origin, you have this special ray going in this point, and along this ray, you don't have a splitting. Yeah, so you have, so it's not a direct product, but it's very close to being direct product. So it's a warped product. And this convergence, so if this is txx, and here this is an x, so we have here kind of, so it's not really a product, but this is close to being a product. So in which, so I want to say a little bit more precise in which sense. So the you can say it in terms of, so you can define it in terms of angles. So the point is the following. So for any point y, which is sufficiently close to the point x, and if you extend this geodesic, you see here another point, say x hat. And now for any point P in your space, if you connect this, then you see two angles, alpha and beta. And if it would be a line in the Euclidean plane, then the sum of alpha and beta would be pi. Now here, just because it's a line, because it's a geodesic, the sum of alpha and beta must be at least pi. Now, if you have a very large branching angle, then it's easy to, so if this geodesic would be, if the geodesic, if xy p would also be a geodesic, then the sum, then alpha would be already pi. And then this alpha plus beta would be just pi plus beta. And then so the statement that the branching angle is not too large just means so that the sum of alpha and beta is essentially pi for any such picture, for any y sitting in this small ball. So this means this almost splitting. Now what we do is we consider maps, so these are distance maps, which are just defined by a few points chosen in the space. And so the coordinates, so this is a map to Euclidean space of some power a, and the map is defined by, so the coordinates are distance functions to points. Now we say that the map is regular. So for some data, so we need some parameters. So if the following happens, so it's regular at a point y. If the following happens, so if you have here the point x1, here the point x2, so if the geodesic from x1 to y does not branch too widely at the point y, so the distance to the point x1 almost splits in this sense of angles at y. The same happens for x2. And these angles are almost, so this angle is almost pi over 2. This, so we need to, to say what, to use some parameter, and we need to make this definition a little bit careful so that the space of points at which such a map is delta regular is open, and such that this openness is stable under Gromov-Hausdorff convergence. So if it's open and you vary a little bit the point xi, or you vary a little bit your space x, then it stays open. So it stays regular. So, and once we have such a notion, then the first basic observation is that such a map at the part where it is regular, it is an open map, and in fact in a controlled way. So it is Lipschitz open. And how do you prove this? So this is rather simple. So if we have here point x1, here x2, here you have this x1 head, here x2 head, and here you have your point y. This point, the map is delta regular. Now what you can do, you have here several, you have several flows. So the flows are very simple. So you have the flow towards the point x2. You have a flow towards the point x1 head. You have the flow towards the point x2 head, and you have the flow towards the point x1. And if you, so this, you just go along geodesic to this point. This is the same as saying you take the gradient flow of this function. So, and now you observe that if you go towards x2, and then the assumptions tells you that you go with velocity 1 towards x2, you go with velocity almost 1 from the point x2 head, and the distance to the point x1 and x1 head almost do not change. This is this first variation. So they change, but at a very small velocity. And using this, you can go so along, so you can go first up, then to the right, then up, then to the right, and so you can reach any point in the neighborhood of the image point. So this proves the openness. Okay, so this is the second tool. And now, so one can say a lot about the fibers of this distance maps. So there are two main observations. So the first observation is that the fiber of such a distance map is locally contractible. So you have here point X, and here you have a distance sphere, and so yeah, so the fiber in this here you have just one parameter, so just one coordinate, the distance function to, so f is equal to dx. So then the fiber, this is a distance sphere, and the statement is that whenever this distance is regular, then this distance sphere is locally contractible. Why this? Now, yeah, the proof is again essentially very similar to what we have seen before. So we have this point on the other side of X, so here is this point Y, and now we take a neighborhood of this point Y and we go first. So if we take a point here, then we first go to the point X head. And then if we cross, once we have okay, yeah, so this does not make too much sense here, just one function. But okay, so for several, so assume there are several points, X, X1, and here we have X2, and here we have X2 head. So we go first towards one point, then we go towards the other, then towards the third, and then so on until we reach this fiber. And again, so since we know what happens with the distances in first order, we can control this process very well and show that a very small ball around this point can be contracted on a ball in the sphere. So it really proves that a small ball in the sphere is contracted. This is the first observation. And then the second one, which allows, which is a main point for all inductive arguments. This is the following. So it tells you, so again, we have here x, we have here the fiber. Right, so, and in general, if you have here a point where at this point, the distance to the point x is regular. So in general, so you could not extend it to a regular function with two coordinates. However, you have this distance function to the point y. This distance function to the point y is regular on a small neighborhood of y. Moreover, here you have a right angle just by the first variation formula. So close by on this fiber, also this angle, they are also almost regular. So nearby, so on this small neighborhood, so if you take this small ball intersect at this fiber, the distance function to x and distance function to y give you a two regular function. And now you can sit in this point and consider the fiber of the distance function to x, distance function to y, and take the fiber. And either, so maybe if you're lucky, it happens that this fiber just consists of one point. But if it is the case, then you have found a point, and the neighborhood of this point will then be really a Lipschitz manifold. So otherwise, you can proceed by induction and find a point in which you have three regular directions, and so on. So this is the main, these are the main tools. Are there questions? So there's another tool I will mention. This is slightly more specific, but these are the tools from metric geometry. So the final tools are geometric topology and homotopy theory. So these are more of topological nature. So, and first is so it's very often easier to control something up to homotopy than up to homomorphism. So, and there's a very general result. So if you have some Gromov-Hausdorff convergence, and so observe, so that here in our setting, so we have lots of Gromov-Hausdorff convergence. So we have, so just if we rescale our space, we have a Gromov-Hausdorff convergence to, okay, so these are non-compact spaces, but still, so we have a Gromov-Hausdorff convergence of the neighborhoods of our space to a cone. Now, so distance, so under this convergence, also spheres, so small spheres around our point converge to the space of directions. And so now the statement is so that if you have such a Gromov-Hausdorff convergence, and if your spaces are uniformly locally contractible, so essentially meaning so that so for instance, if on any space xi, small balls of the same fixed radius are contracted, then the limit space is homotopy equivalent to spaces xi for I large enough. So this is a result which, I think it was before the notion of Gromov-Hausdorff convergence, it was known to Borsuk, and then it was recovered by Peter Peterson. So in our situation, so we know so that small balls are contractible, and small balls without a point one can again use so that that the distance functions are. So for this you do not need actually nothing. So this is true also without the assumption that the space is GCPA. So any punctured ball is homotopy equivalent to the space of directions. Okay, so and then there is another topological result. So this is again okay. So a small contrast with the theory of Alexandrov spaces. So there you have a similar theory of regular distance functions, and there it's a famous result of Perelman, which says that such a regular distance function is a fiber bundle, is locally a fiber bundle, if the fibers are compact. So here it is not quite the case, but so it's since we have already proven that all of our fibers are locally contractible, one can make it uniform. So this result shows that all these distance functions, they behave like a homotopy. So they are homotopy they are local homotopy fiberations. So, and in order
sorry, question. F is a regular map here, right? Or
no, so this is a general topological result. So if you have general metric spaces, say maybe you need to assume finite dimensions. So and you have a proper map. You have a proper map between them. So meaning that the, say, pre-image of compact set is compact. Then in order to say that F is a Hurewicz fibration, you only need to verify that the fibers are locally uniformly contractible.
Mm-hmm.
So this is this tool from geometry, from homotopy theory we use. So, and we apply it to these distance functions. So for us, so this X will be our X and Y will be an open subset of RK. Okay, so and the last tool we use is manifold recognition theory. So this is this is a very deep theory in geometric topology. So yeah, which provides a very efficient answers to the question, how do you know that if you have a space that it is a topological manifold? So and the point is, so you need to control local homology. So you need to control homologies of punctured neighborhood. So your space needs to be locally contractible. It needs to local homology must be as in the Euclidean space, and then you are almost there. Then there is a little bit more that you have to prove. So this little bit more turns out to be if you really have it in practice, so not so easy, but it's not so you know what to do there. So this is a final tool we apply. So this is more or less all about results and tools I want to say. Then I have another page with final questions about this theory I think are reasonable. So do you have questions so far?
I have a question.
Mm-hmm.
For the Borsuk-Peterson theorem here, do I need to have a uniform bound across the whole sequence and on the limit space, or is it that each element of the sequence has its own uniform bound for local control?
It's okay. So what for sure suffices. So if for all xi they are uniformly locally contractible, and there is some fine issue. So you need to assume that all spaces are finite dimensional.
Okay.
A priori.
Thank you.
And the other questions? Okay. Then I would like to just to finish the talk with some other questions. So what one would like to say more about these spaces, what one would like to know. So as I said, There's a regular part, and the regular part, so we have really a Riemannian structure. So one can ask if Riemannian structure is has optimal regularity. Yeah, we don't know it quite, but what is maybe more interesting at this point is finer structure of the space in codimension 1 and 2. I think Koichi Nagano will deliver a talk about this so he has put something in this direction. Then, so something else which would be desirable are harmonic coordinates on large parts of the regular part. So this is something which has been recently established on Alexandrov spaces and on non-collapsed RCD spaces. So I think this would also be very interesting in this setting. Related to this is the control of the so-called metric measure boundary. So as I said, so most points, so the large part is a Riemannian manifold. So most, so infinitesimally, most points, so most small balls looks very Euclidean. So, but now you would like to be a little bit more precise. So to say how many, how similar to Euclidean balls are small balls. One can make this equation precise. So it was recently using harmonic coordinates. It was recently verified that the metric measure boundary on Alexandrov spaces vanishes. Something similar would be desirable here. And related to this, so the existence of a geodesic flow, of uniquely defined geodesic flow on a large part of the space. So this would also have implications to the geometric group theory. Okay, so and the final, a simple-minded question is: so if being GCBA is a topological property, so meaning if you have, so I'm rather sure it is the case, but I don't have a proof of it. So assume you have two Riccard-Kappa spaces. One of them is geodesically complete, and they are homomorphic. Then the other one should be geodesically complete too. So the statement should be in a sense. So it should be something like not having three faces. So, but it's not. So that's all I wanted to say. So, thank you very much for your attention.
Thank you. Questions?